Hello, Professor Sargent here with you again. We're going to take a look at one more example of applying the Simplex method. Applying the Simplex method to solve a standard minimization problem. Took me a moment to remember that. It involves rewriting the problem as a standard maximization problem, and then reading these final simplex tableau a little differently. It's something I showed in an earlier video, and we're going to get to see that again here. There we go. All right. So here is our standard minimization problem to solve. That's our first original problem, what is being called the primal problem. And we're going to turn that into a dual problem, which is the standard maximization problem. So first we look at the table of coefficients. This table is not a simplex tableau. That's the table of coefficients from the primal problem. And we transpose that. Each row becomes a column. So row 1 becomes column 1, row 2 becomes column 2, etc. And we use the original variables as the slack variables for the dual problem, which is a standard maximization problem. So reading from the new table of coefficients from the transpose, here is our dual problem, the standard maximization problem. And we're going to add in slack variables, but those will be the original variables for the primal problem. Now we can set up the initial simplex tableau. And we do have negatives in the bottom row, the objective row. So which one has the greatest absolute value? The negative with the greatest absolute value is in column 1. That's the most negative entry. So we're going to take the entries in the far right from the other rows and divide them by the corresponding entries in that pivot column, column 1. And the smallest of those two is the 4 coming from column 2, sorry, from row 2. So we already had that column 1 is the pivot column, and our pivot row is row 2. Since we have a 2 in the as the element or the entry at the intersection of column 1 and row 2, we're going to multiply that by 1/2 to turn it into a 1, but we have to do that to all of row 2. And now that we have a 1 for the pivot element, we're going to use that to affect the changes in the rest of the column and turn that into a pivot, turn that pivot column into a unit column. So these are the two other row operations we will perform. Here's what we get. And I'm going to try to also show this on the TI-84 and the on Excel as well. But for the moment, here's what we're getting. And now we still have a negative in the objective row. only one of them. So column 2 is going to become our new pivot column. Take the 4 divided by the 2 in row 1 and the 4 divided by the 1/2 in row 2. Look for the least positive ratio. And that comes from row 1. So we've got column 2, row 1. Row 1 is our pivot row. And since we have a 2 as the entry in the pivot column, the intersection of the pivot column and the pivot row, then we're going to multiply everything in row 1 by 1/2 so that that 2 becomes a 1. But we have to change everything else in the row as well. And then we've got a positive 1/2 that we're going to have to turn into a 0 in row 2, and a negative 1/2 in row 3 in that same column, column 2, that we need to turn into 0. So here are the new row operations that we'll do to change row 2 and row 3. Here's what we get. There are no longer any negatives in the objective row. So we've reached our optimal solution. You read it one way and you'll get your solution to the dual problem. That would be the way that you first learned about. But also from the same final simplex tableau, we're also finding our solutions to the primal problem. So here are the coordinates producing the solutions. And for the original problem, the primal problem, x is 1/4, y is 5/4, and we get a minimum value of c. And that's all I've got to say about that. Hope it helps. Stay safe and healthy.